Let's see. So the quiz everyone did pretty well on, except one group didn't get it at all. So everyone got 80 or 90s and seemed okay. This is the answer part. So it's just similar to the example, example problems in some of the old quizzes. The problem people had, I think, was just with this part E, because you're starting with a vapor stream. So feed stream is 298 and 0.8. The feed stream's a vapor. So that, and you're given the heat of vaporization, so you have to subtract it from the vapor stream, not add it to the you have to subtract it from the liquid stream, product stream, not add it to the vapor stream. So you're feeding in a vapor in this, so you had to, that was the only thing. And then, so nobody got that, but basically that ends up, I took 5 points off on from everybody, I think. So that was the only issue with the quiz. So a lot of people got 95. Otherwise, seemed okay. There weren't many questions either, so I think mostly people were okay with this, unless you guys have some questions or if there's anything I can go through it, but it seemed like it was okay. My chat doesn't bing when you send a chat, so I basically, the only way to get my attention, I think, is to say something. You can send in a chat to say, you have to verbally say, read the chat, I think, because it doesn't bing. And I put into the preferences that it should make a noise, but it didn't. It hasn't done that. Anyway, I put over on the web page, if you want to look at it, this separations book up here, like separation processes. It's an old book from the 80s, but 1980s, but it's got like chemical engineering separations. Because this chapter deals, chapter 10 and 11 are kind of a coupled chapters dealing with basically distillation, right? So, or the background that you need to do distillation. So anyway, the separation book might be helpful to glance at. It's got a lot of chapters on distillation that you can look at, but it's not really much more in depth than what's in our book. So I wanted to, this week, I want to finish, chapter 10 we didn't finish, so I want to kind of quickly finish it. And then chapter 11's coupled with chapter 10 is just for non-ideal, like non-ideal behavior. So the activity coefficient. So the two chapters are pretty much tied together. So it's okay. And we don't usually have a split week like this. So that's kind of one of the issues with this. We're running the semester now. Anyway, I think you did homework problems already. You finished the homework for chapter 10, so you must have done the problems with headspace and tanks and volatile organics. So usually you have to do a calculation to figure out what you're releasing to the environment, and there's some kind of spec for the maximum amount of volatile organics you can release, and it's variable with different kinds. So you have to kind of look up in a table what's an allowable emission for a length of time. Right. So especially if you're going to have empty tanks that you need to flush out. And also, as you fill a tank, there's going to be release of the headspace gas. And this stuff is all basically just use the saturated pressure and then ideal gas equation. That's mostly what how these are dealt with in this book, in this chapter. It's good that he mentions this because it's something you'll definitely run into. But this is, I think, just kind of logic to do these. And you've already worked the problem, so hopefully you know how to do that. This one is of the venting things, this is the most complicated, right? The idea of how long, so if you have a tank, so you have a some kind of a tank and it's been drained. So you drained out all the fluid. So it's empty, but it's got like PSAT for your components inside of it. And then you want to flush the tank out to remove the volatile organics from it. So how much time to like reach YI is less than death. Like you have some level concentration of toluene that you can go into the tank to wash it out. And if you get above that concentration, you die. It's basically you want to know how much time it's going to take to get to that concentration. So you're going to be flushing with some kind of volume, and the tank itself has the volume. And then you want to know what's the time to do that. Right, so you can say, I mean, you're going to have your concentration of your deadly chemical in time, and your starting concentration is going to be related to PSAT by P, so atmospheric pressure, and the saturated pressure is your starting thing. Then somehow it's going to drop with time until it reaches some kind of safe level. So in this case, it'll never reach zero. Like you can't reach zero concentration. So you have to define like what's safe, like 1 parts per billion or something, some small number. And then there's going to be some way to connect that, and it's going to be an exponential decay, right, to get to that point with this flushing. So basically, you want to know, the rate of change of Y with temperature, with time, right? So that's going to, so as your concentration drops, so the slope of this decreases with time because you have less Y, less say benzene in the tank as the time progresses. So this thing has to be proportional to the amount of benzene in the tank, like YI. And then it's also going to be the kind of the rate of the decay. So dyi dt is also going to be proportional to the flush rate. So whatever sweep rate that you're using. And the bigger the tank, the slower that decay. So the tank volume. And so that's just kind of logic. So that the rate of decay depends on the amount that's in there. So anytime you have the rate depends on the amount, you know you're going to get an exponential or a log out of that. Because you're going to rearrange it, dyi over yi equals the sweep of tank volume times dt. And then you integrate that, dy over yi gives ln y final over y initial, yi initial. And that equals the sweep rate over the volume and then the time that you gave it. Then you get this, you'll just get this exponential. The final is this exponential decay, which is the thing you would have guessed anyway at the start. This is an exponential. It's going to be exponential minus the rate over v times time. So then you can calculate how much time by taking the log of the final, the desired living concentration that you can live with, and then the initial from the saturated pressure, and then that times the volume of the tank times v dot of the sweep gives you the time that it takes for that to work. So that's the kind of calculation you can expect to do. Like basically all the time. You want to estimate how long it's going to take to make something safe. It's just the same as a radioactive decay kind of thing, you know? So it's like an exponential decay. That's important. And then the rest of this is pretty simple. I think you've already done problems on it. So you heat and it expands and you figure out what the final concentration of the headspace is going to be. Let's see. Depressurizations. I think you've done some problems with this. It's handy that he's given these things. I mean, this thing is important, this flashpoint calculation to see, to determine the danger of being in the tank, right? So anytime you're involved, like even if you have any metal at all, metal on metal will make a spark and then you get an explosion, but explosion can only happen. So explosion means you're making a fire, right? So to make a fire, you're gonna have to have like that's right. So you have to have oxygen and some fuel, and then you're gonna have some products that come out of it. So you can have like too little fuel, and then this won't happen. And you can have, so there's going to be some Y of methane and some Y of oxygen. And it turns out like you need a certain amount of fuel and oxygen. So if your fuel is too low, you won't get combustion because the heat won't be enough to continue the reaction. Right? In other words, this reaction is going to release heat. Right? And that heat drives the reaction. That provides energy to initiate the reaction because there's energy barrier. So you have like energy of the reactants, then it goes up, and then it goes way down. So you have this change in heat for the reaction, but there's also this energy barrier. To overcome that energy barrier to make the ignition happen, you have to provide heat. Heat comes from the reaction. So if you don't provide enough fuel to generate enough heat, you don't get over that barrier and it doesn't burn. Right? So there's a minimum amount, concentration of methane in order for that reaction to happen. There's also a maximum amount because if your Y, you have to have 2-to-1 methane oxygen. If you get too much methane, there's not enough oxygen and it won't burn. Because it won't burn, that cools down the reaction. So that methane didn't burn, actually cools the whole scenario. And with that cooling down, you don't get above that energy barrier either. So you can either have too little methane, so you don't have enough heat to get over that barrier, or too much methane so that you cool it down so you don't get over it. This EA has to be KT. It has to be generated by temperature. The temperature comes from burning the methane. So you put in so you can have too much or too little. So there's going to be a window in Y methane where you have at a certain temperature and ambient temperature where you have combustion possible. So too much fuel or too little fuel both work to kill a fire. If you flood it with fuel, you will kill the fire because the heat capacity of the fuel will absorb the energy and it won't get above the activation energy for the reaction. So anyway, you have a lower flammability limit concentration, so you want to watch out for that. So if you're in your tank and you had benzene in the tank, but you drained out the benzene, so then the tank is full of benzene vapor at Psat. Is Psat over P greater than the Y concentration for LFL, the lower flammability limit? If it's above the lower flammability limit, then you're in trouble, right? Then it could blow up. Then the entire tank is a bomb, right? This is gonna be dangerous. If you're above the lower flammability limit, it's okay. So if you think about, you're gonna pump like natural gas in pipes, then you're way above the flammability limit. It can't burn. So you're pumping like propane in a pipe. It's almost, Y is almost like 99% or 0.99, right? And you're in the upper flammability limit is going to be something like this. So it's going to be something like 60% or 0.6, right? Because you're 0.99 when you're pumping natural gas, you're safe. But if somehow you get a leak, somehow oxygen gets in here and it gets to 0.6, then all of a sudden you have a pipe bomb, right? Running through your neighborhood. So basically, there's an upper flammability limit that allows you to pipe natural gas around a neighborhood without an explosion hazard. There's a lower flammability limit that you're really considering when you're doing this tank thing. Like you have saturated vapor in a tank, you have to be below the lower flammability limit. So you calculate those with this PSAT. It's the same thing we've been doing. So that's included in chapter 10, and there's some homework problems to do that. So I think that's hopefully that's kind of okay. Then so chapter 10 kind of carries a bunch of different things. So the other thing is distillation. He goes into it in a little bit more detail here because he's got these K ratios now. So anyway, this is the lab distillation from chemistry lab. So you have a reflux going on. You boil the fluid at the bottom, they reflux. So this is basically at saturation, right? And then you carry off the vapors, you can condense it into a liquid. And the composition of what's in the boiler to what's in the condensate are different, right? This is richer in the light components. Right, so you have the heavies here and the lights here. Right, so you can, if this is a mixture of a bunch of different things, you could have a heavy key component. So you call it heavy key, and you have a light key component. So the light key, so you can have a separation ratio, which is the distillate, the composition of the distillate over the composition of the boiler, right? And if that's greater than a half, you want that greater than a half for the light key, and you want it less than a half for the heavy key. Say you have 10 components in the boiler, then you want to have the one closest to the middle in terms of the boiling, the saturated pressure. So that the lowest saturated pressure would be on the heavy end, but the highest saturated pressure would be on the light end. You want two components that are near the middle, right? That's going to be your key. So you have 10 components. This is the saturated pressure. It's increasing towards the light. You want one heavy one and one light one. So a heavy key and a light key. That you know that everything heavier than that's going to be in the distillate, and everything lighter than that's going to be in the distillate, and the other one heavier than that's going to be in the boiler. Right. So you're separating the thing, and all these components go that way, and all these components go that way. So all the heavy components go to the bottom, and all the light components go to the top. That's the idea. So the heavy key and the light key give you two flags. If you separate those to this 50%, then you know all the other ones are going in the right direction, and all the light ones are going in the other direction. So that's kind of the idea of this. If you have a mixture of things here. So each of the stages in a staged distillation column, which is only one type of distillation column, are going to be like this boiler. They're going to have a liquid and a vapor in equilibrium. So this L11 and V12 are in equilibrium with each other, and their equilibrium set up on this tray 12, right? And then tray 12 is condensing vapor 1,2 into liquid 1,2. It's in equilibrium at tray 13. So each of these trays is like this distillation column. It's like having 3 distillation columns like this. Then here you'd boil it again, and then you'd have another one and another one. So it'd be 3 trays, three of these lab setups. Or you could run the lab setup 3 times to do this same thing. If you say you doubled the amount of trays, or you tripled the amount of trays, or you made these infinitely number of these trays, then this whole thing could just be beads. You could have a packed bed column full of beads or some odd shaped objects, right? They're going to allow this kind of operation to be happening continuously instead of in stages. So there's different ways to go at this, and you'll learn, I guess, in the separations class, like why you'd use one over the other. But basically, the easiest one to figure out is if you have stages, because each of the stages you can calculate the equilibrium on it. in the same way that you could calculate the equilibrium here. Right. So when you look at the when you look at this in terms of the temperature composition diagram, so we have liquid here, that's the bubble point at the bottom, and it's the dew point at the top, right? And this is pressure they switch. Okay, so for pressure, the bubble point's at the top and the dew point's at the bottom, right? So, and if equilibrium means they're at the same temperature, so if you're on one of these trays, it's at the same temperature. So the temperature drops as you go higher. So the more volatile things are at a lower temperature, right? So each of the stages is kind of one of these lines. And then the condensation that happens is this drop, right? You go from vapor to liquid with the same composition. So that's like when you're going from vapor to liquid. So your vapor goes up and then it turns into liquid up here, right? So that's kind of the vapor going up and turning into liquid is that drop. This is the change. That's the delta H to condense. Right, and that delta H is used to boil the next tray. So then you get the equilibrium between the liquid and the vapor and the horizontal, then the condensation of the vapor, then the vapor liquid condensation. You can see as you do that, you can start with one composition and end up with another composition. So you start rich in whatever B component, and as you march along, you end up rich in the A component. So that's how distillation works. And this is the kind of diagram you can see. It's going to take more and more stages to get purer and purer, right? So this becomes like an infinite loop here as you get closer and closer, just jogs there. So what you can do is instead of looking at temperature composition, you can plot this as the X, so liquid, and the Y, the vapor. Right, so you have Y vapor versus X liquid. And each of these equilibrium points is a point on this thing, right? So depending on how you have your, see, and it's also going to look like this step thing, similar to this, because this is called the McCabe-Thiele diagram. And this is the no relation to the Thiele in our department, I don't think. You can ask them. But anyway, so the idea is that you're going to, if you get to the top of this tower, then you have like a reflux ratio, right? The split that happens here. So you have vapor coming off, and then you're going to condense it. So you could make a vapor product, or you can make a liquid, usually a liquid product, right? So that you can do something with it. So the total condenser, so you're going to make all liquid product, and then that could be totally fed back, right? So this R ratio, D could be 0 and R could be infinity. Or you could say, I'm not putting any liquid back. And then then L by D is 0. So this reflux ratio can be infinity to 0. Right? If you're just making product, it's 0. And infinity means you're not making any product at all. So product is why you're running the distillation column. So basically you're going to have some D, so it's not going to be infinity. Right? But in this McCabe-Thiele diagram, so if it is infinity, meaning that you're fluxing everything back, then this is a straight line, right, where X equals Y. And then the other point is the equilibrium points between Y. So all the points on this chart, X and Y, so X to the left, Y to the right, that gives you Y versus X, gives you this curve, right? So says that, but all right, so so these are each different temperatures here as you go up, right? So to do this operation, you have a relative volatility. So Ki is so you have different components in the system. This is for a binary Ij, or if it's a mixture, you'd have like the heavy and light. So it'd be alpha HL. That would be KH, K key H, KH, or K key light, KL. That starts to get confusing. Let's see. I got that right. The whole thing's a little confusing, but so you got an LK and H. So it'll be it'll be light key over heavy key. So LKHK, KLKKHK. And then this alpha will be alpha LH, light heavy, right? So that's a relative volatility between the two key components, and that's the thing you would map out to see how the separation is going to work for if you have a mixture going into a distillation column. Anyway, so so then what about the rest of this? So there's this operating line for no reflux, and there's a real operating line for the system. Then there's this point where there's a pivot between the two lines. So in other words, you have some product being made, so you're not along this R infinity line. So you have these other lines. So what are those other lines? The other lines come from, and you go through this in separation. So we're not becoming experts at this here, but it's just give you a rough idea on the terminology. So you're feeding into your column, not at the bottom. So you don't just put it in the pot like you did when you have the lab. You just put it in a pot and you boil it, and that's it. But here you're going to have like not one of these. You're going to have like 12 of these. 12 of these. Each tray is one of them, right? So your feed that you put in isn't going to be at the highest temperature. It's going to be somewhere in the middle. It's going to be more efficient to separate it that way, because that allows you to separate the heavy keys to the left and the light keys to the right, or up or down in a tower, right? So otherwise, the best concentration you could get is kind of what you fed in. So if you want to do a separation where you purify the heavies and purify the lights, then you feed in the middle of the tower. Okay, so the normal operation is to put your feed in the middle and let it kind of trickle down to the bottom and then rise up to the top and do your separation that way. So in that case, so this is how that works. If say your feed is half vapor, half liquid, and the vapor liquid match. So the vapor liquid are going to be composition are going to give you like 0.6 and whatever here, right? So whatever your feed composition in terms of liquid is fraction, then you'd go straight out 3, right? If it's pure liquid that's being fed, then you go straight up. And if it's pure vapor that's being fed, you go horizontally. So depending on the composition of your feed, you find the feed composition, like the Z for the feed composition, and you go to here, and then you're going to go across this line depending on the state of the composition. And that decides on the slope of the two curves and the pivot point for this. And then this is your purification of the heavies. This is your purification of the lights, right? And then they're going to be at equilibrium. That's the equilibrium point for the feed tray. And each of these points is a different tray in the distillation column. And then you're changing composition to the next tray and the next tray and the next tray, like along the staircase. Right, so that's kind of, this is just from Wikipedia. So basically this is also in that separations book that I put on in a little bit more detail that I put on the webpage. So you can look at that. Basically, you can glance through that if you're interested. So of the separations, 80% are going to be done with this kind of thing in a chemical plant, right? And that's going to account for 70% of the operating cost. It's basically this kind of separation thing is most of the job of the chemical engineers at a chemical plant. It's going to be involving these kind of things. That's why separations is an important subject. But for our purposes, it's an example of how you use thermodynamics. So it isn't necessarily the core competency for this class. What else is in here? There's this estimation equation for ideal solutions for how you get how many stages you need in a column. But you can do a calculation. I think there's a homework that uses that equation. But that's kind of all I want to go through for that stuff. Hopefully it didn't take too much time, but it's just really a glance at it here. It isn't necessarily, you aren't supposed to become an expert in this class. Like the separations, you'll become an expert in this. So this is also mentioned. So chapter 11 is about how you deal with non-ideal systems, but this just introduces the terminology of it. Right, so if two things are similar to each other, like benzene, toluene, then they follow basically Raoult's law, and they're going to have kind of a normal behavior that we've looked at so far. Right, temperature, compositions, you can see that it's kind of, there's no deviation from Raoult's law. Like a straight line is right in the middle of this, and you have the separations going on. Right? And the same, like the pressure composition has a straight line, it follows Raoult's law. So basically you can have deviations from this. So they call it like a positive deviation, like propanol water. So it's going to look like this. And you can have a negative deviation. So this is chloroform, acetone chloroform. So the straight line is Raoult's law. The pressure is proportional. So the vapor pressure is proportional to the composition. Right? And then these are deviations from that. Positive deviations when the two components. So here propanol likes to be with propanol, water likes to be with water. That gives rise to this positive deviation. And acetone prefers to be with chloroform rather than with acetone. So that causes this negative deviation. So this theory, along with why this happens, in other words, you can kind of predict which kind of deviation you would get. The interesting thing is, so we look like if you were looking at this step thing to do the distillation, so step, 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 step. Well, if you have one of these deviations in this thing, so you can do your steps, and then all of a sudden you're stuck here because y equals x. Like at that composition, at that feed composition, y equals x, you can't separate it. So that's a dead end point in separations. That's the best you can get. So that's an azeotrope that causes this problem. So you can break an azeotrope by adding some other component in that separates these two curves. Right, so that would be one approach to breaking an azeotrope. Add in a component that makes this curve change, like something that breaks up the attraction between propanol and propanol, or breaks up the attraction between acetone and chloroform. A third component that interferes with that. Then you could break the azeotrope and get through to the other side. The other thing is that the XY. So here, y is smaller than x. This is pressure. X is smaller than y on the left-hand side of the azeotrope. On the right-hand side, y is smaller than x. Y is at the bottom because this is pressure over here. Right. So basically, the y, x, and xy change relationship across the azeotrope. So in that way, you can tell if you're going to have an azeotrope, if you have one temperature or pressure at the low end and one temperature or pressure at the high end. And if the y and x change, y is bigger than x or x is bigger than y on the two sides, if that changes, then you know there's an azeotrope in the middle. Right. So next chapter is like how you deal with this mathematically. So we'll deal with that. Here it's just to say positive deviation, negative deviation, the word azeotrope, minimum boiling azeotrope means it's maximum pressure, because the T composition chart is the opposite of this. It's going to be below. And then negative deviation means maximum boiling azeotrope, means the temperature composition one will be above. So I'll show you those in a second. Here, so this is this is the propanol water. So this is one we just looked at. It's got a high pressure and this low temperature, right? Minimum boiling. So you can, when you get to boil it, the azeotrope has the lowest boiling temperature. And the opposite is true. You have the highest boiling if the pressure's below, like chloroform acetone system. So again, this is just terminology here to talk about this. This is the chloroform acetone. And then that's about it for that. it's just to introduce the terms, and we'll describe it in chapter 11. So maybe today's somewhat, but right then there's this thing that's usually kind of a separate chapter in a normal thermal class because it's engineering. It's like less emphasized. So we had these equations like from the we had the we had this guy, and then we said, like, if you want to say Gibbs free energy, so the changing Gibbs for boiling is going to be H minus ST. Right, so like that. So you can say that you can say that like a change in Gibbs is going to be or let's see, that's not what I wanted. That's something we need, but that's not what I wanted. G is minus S, so dt, so the corner thing, like that, and then V dp. So you can say like dg equals, so this is dg already, right? So S minus S is dg dt at constant P. And then you have V is dg dp at constant T, right? Because that would just be like a expansion of this, right? From those two parts of this. So say you're at a say you have liquid and vapor, right? And then we're talking about like the vapor pressure involves like an atom going from the liquid, or a molecule going from the liquid into the vapor, or from the vapor back into the liquid. So that's what we talk about in terms of equilibrium, right? So if you have one atom that's going to jump up into the other phase, and you have like, then there's a change in the free energy of the system with respect to that atom changing the phase. So you need, instead of G, the intrinsic number, meaning per mole, then you need the extrinsic, which means just the value, like G bar, G underscore, right? Because if you're changing the moles, you need to consider G underscore, right? And then you can write this same equation, this business for G underscore, except because it's the actual value, not the per mole value, right? Then you can say GdP and then GdDT. So this is minus S, that one's V, or this one's minus S and that one's V. And then because this isn't per mole, you can say the change with that atom jumping out, like how does the Gibbs free energy change when the atom jumps to the other phase? Right, so that free energy change when the atom jumps to the other phase, dg underscore dni. So say in the liquid, that's called the chemical potential. That's the definition of it. So we have this chemical potential term showing up. dg/dn, everything else is held constant, including the other components, the composition, and then dni, that component. You're going to sum over all the components in the system. So that sum will be just the chemical potentials of the system. And we showed already the chemical potential is related to the fugacity, this log of the fugacity, RT log fugacity. Right, so this is just showing, this is the norm, this is the full equation at an equilibrium interface. So we know that like the chemical potentials are equal. In other words, the chemical potential of component 1 in the liquid phase has to equal the chemical potential of component 1 in the vapor phase. That's the definition of equilibrium, meaning that to take an atom or a molecule in liquid and put it into the vapor involves the same change in free energy as to take the atom or molecule from the vapor and take it into the liquid. That's what this equation means. So that's kind of how this thing works. Okay, so that's kind of important, but not in any like homework problem or anything. It's just like a basic thing that's usually emphasized, you know. In this book, it's just a side at the end of the chapter. So you rewrite all these equations we had before into this idea that they can jump from one phase to the other. So you can talk about the chemical equilibrium between the two. You have this equilibrium terms for two phases. So you have this number for your one phase liquid, also another number for the, so this chemical potential is going to have two things with it. So you get UI has to be I, and it's got to have a phase. So each chemical potential is going to be you of benzene and liquid, you of benzene and vapor. And those two are equal at equilibrium, but they don't have to be equal if it's not at equilibrium. And then you're also going to have U of toluene and vapor and U of toluene and liquid. So if you have two components, like a binary solution with the two phases, you have four chemical potentials, right? And two of them, two pairs of them are going to be equal to each other if it's at equilibrium. So every time you say chemical potential, you have to say what phase and what component. You can also have a chemical potential for a pure system, right? In other words, you wouldn't have components if it was just benzene, but you would have still two phases, liquid vapor. And you could have liquid vapor solid. So that's kind of how this chemical potential thing works. What else? Equilibrium criteria, and then he just says this thing like the chemical potential. So this is for when it has a hat over the fugacity, that's a component and a mixture. So the fugacity of I is just for pure. Then fugacity with a hat means that component and a mixture, right? And then this is just what we had before, that the chemical potential changes the change in the log of the fugacity. We had that, or the log of the fugacity is a chemical potential. We had that before. And so it's just reiterating that. And then at equilibrium, the component fugacities are equal. And then we got that 1060 equation that was in the quiz from this kind of business. Wherever that is, this, that we can say that it was 1060 in the quiz. Let's see. Yeah. Quiz. $10.70. This business. This is also. So we're getting the pure component fugacities, and we get the Y and X. That's kind of worked through at the end of the chapter. So I don't really want to dwell on this because it's kind of odd, you know, a little bit that mostly chemical potential is pretty easy to work with, and that's what chemists work with. And the fugacity gets to be pretty complicated. I'm not sure. You can always relate it back to chemical potential. So that's kind of the idea, like try to understand chemical potential as equal at equilibrium, and then the fugacity is also equal. And then there's some general rules for fugacities. You can just kind of use those if you run into it in a problem. I think that's the main idea here. That's 1070. So that's our thing for equilibrium. So that's about it for chapter 10. That's all I want to do on it. There's a little bit more, but basically, if you want to read it, it's okay. But I'm going to bury chapter 10 for now. What have we got on time? We got 10 minutes, I guess. So I want to talk about how to deal with these deviations. Okay, so I can definitely do it in 10 minutes. So you can have Boltzmann's law, right? Basically says that you have a probability is going to be related to Gibbs free energy over KT or RT. So the probability, if there's some kind of change in energy that happens related to KT, the exponential and negative. So if that energy is 0, exponential of 0 is 1, so the probability is 100%. If there's no energy barrier, then it's absolutely that it will happen. And if this energy barrier is infinite, then that probability goes to 0. The bigger the energy barrier, because it's negative here, the lower the probability. Right? So that's kind of logic. Right? So if you have a mixture of A and B, the probability of finding A is the XA, the composition of A. Say it's in a liquid state. Right? So, or a gas state. Right? So if the probability is XA, and if you have, we had before delta G is delta H minus T delta S. So if we say there's no enthalpic interaction, we only have entropy. So we're going to consider that the atoms can pass through each other. There's no enthalpy of interaction at all. There's no repulsion. There's no excluded volume. Right? This thing is 0. Then you just have this term, and then you can say that. Then you can say that the S part of this thing of mixing over R, because it already has a T in it, is ln of X for component, say A, in a mixture A, B. Because of this exponential of the argument, and it's by KT, the T gets taken out. And it's just going to be ln of the probability, which is XA, equals this, and H is 0, so it's delta S over, and it's S times T over K. That's this thing. And then if you have a mixture, so you say you have A and B or whatever you want, you can say that delta S over R is going to be just a rule of mixtures, like the amount of A times the entropy of A plus the amount of B times the entropy of B. And so that's ideal mixture. And if you say that you have delta G is delta H minus T delta S, delta H is 0, then you can say that delta G, the change in free energy, is XA ln XA plus XB ln XB. Right, so that's the free energy for mixing of an ideal solution, and that's going to follow Raoult's law. That's an ideal mixture, right? That YA equals P sat A over P. Right? That's our ideal mixture situation. So this isn't an ideal mixture because we have a positive deviation from Raoult's law. Right? So we're going to have something else going on here. So how you describe that is you say, I'm going to have an enthalpy. I'm going to make up an enthalpy, and it's going to be a binary enthalpy. So we have delta H equals, and the odds of an A meeting a B are the probability of an A times the probability of a B. So XA, XB. I'm going to multiply it by some number that gives me the enthalpy of that interaction. Like what is it? What is the energy of the interaction of A, B once they meet? So once they meet, XA, XB is once they meet, they give an energy omega. So that's called a Hildebrand interaction parameter. And it's the same thing as a Margulis interaction parameter. So one parameter Margulis interaction parameter. So XA, XB, then you call it A12 or AAB for a Margulis interaction parameter. And then it's also the same thing as for polymers, you call it XA, XB times this chi parameter, chi AB. So there's different terms that are used for the same thing. Margulis is A, omega is Hildebrandt, and chi is Flory-Huggins. There's some nuances to these. Basically, at least Hildebrandt and Margulis are exactly the same thing. The one parameter of Margulis. Margulis will have multiple parameters. And then you can get it more complicated, but this actually is a pretty good setup to do this whole operation of looking at non-ideal situations. So then you have delta G is XA, and let's call them 1, 2, ln X1 plus X2 ln X2 plus A12 X1 X2, because the book uses 1, 2. So then you have, so that's this business, right? So you can get this idea that you have that business. Okay, so then the next thing is, say instead of, so another thing that people, the probability is X1, X2. So probability, because when I have isopropanol and water, the isopropanol likes to be with isopropanol and the water likes to be with water. That's why it gets a positive deviation. So I can say, well, it isn't the composition that's the probability, because that attraction between isopropanol deviates the probability. So I make up a new thing as like composition, but I call it activity. So then that activity, I say this real thing. So this is called the excess, delta G excess, and this is the ideal. So you can say that delta G is ln A, the activity, plus X2 ln of A2, activity. And then the activity encompasses this Margulis parameter. And if you want to go further and say, well, I want it in terms of X1, X2, then I can say X ln, and I have an activity coefficient 1, X1 plus X2 ln activity coefficient X2. The reason you want to do that is because then if you want to talk about the excess free energy, then you have A12 X1 X2, and then because ln of something times something is ln of something plus ln of the other thing, then that will be X1 ln of gamma 1 plus X2 ln of gamma 2. So your excess, which is this excess term up here, becomes this expression with these activity coefficients where gamma 1 equals activity 1 over X1. So you have the activity and the activity coefficient. And then you have this Margulis coefficient, and they're all related to each other. Right. So how would you calculate it? Like if I know A12, say I know that, then how do I get gamma 1, like the activity coefficient? Right. So you get that by this. So you say this XS is going to be the sum over XI of the ln of the gammas. So then you could say, if I have the molar, like this is the extrinsic Gibbs free energy XS. So that's the number of moles times the intrinsic. So the Gibbs free energy per mole gives me this extrinsic. Right. So this is the actual value. The change in that with respect to N gives me the chemical potential. The change in the actual value versus removing one of them gives me the chemical potential. That chemical potential is this ln of this activity coefficient. Right. So, and this thing can also be calculated in terms of Margulis, because this G is the Margulis times X1, X2, and this thing times N gives me G, so N times that gives me this. And then if I multiply that out, I have A12, so N times X2 is N2, and then N1 over N is X1. Then I can do the derivative of this to get this thing, to get the gamma. And if I do the derivative of that, I get two terms. The first one is N2 doesn't depend on N1, but N1 does. So this becomes N2 times 1 over N1. Then taking the derivative of the second one is 1 over N squared times N1. These both have an N in it. You pull that out, N2 over N is X2 And then this thing inside this is x1, so it's 1 minus x1. 1 minus x1 is x2. So you end up with ln of gamma 1 is a times x2 squared. And you can do the same thing with swapping the numbers and find ln of gamma 2 is a times x1 squared. So if you have a12, then you can get, then gamma 1 is going to equal exponential of a12 times x2 squared. And gamma 2 is going to equal exponential a12 x1 squared. Or if you know one activity coefficient, like at the azeotrope, then you can get a12. But if you know the azeotrope where x1 equals x2, or x1 equals y1, then you can get a12 from that. So we'll go through examples of how you use these equations, but that's basically in 5 minutes kind of what this chapter is about, is basically getting these activity coefficients and then calculating from these kind of curves. So these lines actually are the Margulis one parameter fits this thing. Right? The lines, the data points are the dots, and the lines are using that activity coefficient approach. So this approach works well to describe a lot of different systems. All right, so why don't we quit there? So any questions or anything I can answer?